back to another episode of It's Dr. Dan, and this time we're going to be going through electronegativity and polarity, which can be one of the more confusing concepts for a lot of students when it comes to chemical bonding. So, when you learned about this picture of bonding, there's two major types of bonds. There was ionic, which was all about giving and receiving electrons, and then there was covalent bonding, which was about the sharing of electrons. However, one thing that you probably found out in your chemistry class was that covalent isn't always this equal sharing of electrons. That a lot of times it's about this, sometimes it's not always even. If you've ever split something with somebody that you might have, like, maybe they took a few more or something, maybe it was even, it's not always the case. So let's learn about this periodic trend and we'll go through some examples, some analogies of what this looks like. So you might have seen an electronegativity chart, something like this, where it's showing the periodic table and all of a sudden there's all these different numbers and values. And what this is reflecting is that different atoms tend to be a little more greedy when it comes to electrons. And it has to do with their valence electron levels. So something like fluorine, for example, that has 7 valence electrons, oxygen has 6, nitrogen has 5, carbon has 4 valence electrons in that outermost layer. So fluorine, it really wants to get that octet. It's willing to do whatever it can to get that last electron. And because of that, it's going to lead to uneven sharing across covalent bonds between different atoms. So, what we see here is in this trend is that there is an unevenness towards the top right of the periodic table. So, electronegativity is going up and to the right. And this trend is following the same thing that ionization energy had, meaning that these atoms are not willing to give up their electrons. In fact, they're on the border of becoming ionic is how much this uneven sharing is. So let's look at that and try to understand this trend and see if we can, how will it be applied. So most of this has to do with bonds. In fact, polar covalent bonds. And what this looks like is it's very similar to a tug of war, or almost like you're on a seesaw between two different atoms. So I have a few little images here just to kind of illustrate what this looks like. So the first one is between carbon and carbon, the same atoms. So what would that look like? Well, being that they are the same atom, they're going to have the same amount of pull on each other across the covalent bond. And we can prove this with electronegativity values. So if I look at this chart, we can see that we have for carbon a value of 2.5. So what can we do with that? Well, we can try to figure out the difference. So if 2.5 is for one carbon, 2.5 is for the other, well, what is the difference between them? Well, we can do some little simple math where we take the bigger value, even though they're the same, subtracted by the smaller one. And we see that, oh, when we subtract them, it's 0. So what that tells you is that we can go to a chart and see that, oh, there are labels for what that difference is between them. So being that this is less than 0.5, this is a non-polar covalent bond, meaning that it's an even sharing. So it's something that's, you don't see more electrons going towards one side versus the other. So what does that look like in terms of orbitals? Well, if I have these two carbons that are bound to each other, and I draw a little electron cloud around them, it's going to be a nice, even type of distribution of electrons across that cloud. So it's nice and happy. It's nice and nonpolar. So this is exactly what these different species sort of want. They want to try to be nonpolar if possible. So, and that's what we're seeing here. Now, what about carbon and oxygen? Well, we know that the value is 2.5. Now, what about oxygen? Well, once again, you can probably take a guess based on the image, is that the girl on the right is kind of taking more of the electron milkshake than the guy on the left. And that's because the trend is it's going up and to the right. So, oxygen is more polar. So we're going to see that, oh, this is a 3.5, which is a lot higher. So what we can show for ourselves to prove it is we take the bigger value, which is 3.5, and subtract it by the smaller value, so 2.5, and what we will get is a difference of 1.0. So what that tells you is like, all right, if we look at our chart again, is that falls right into the polar covalent area, meaning it's uneven and most of it is going towards oxygen in this case. So whenever we have something that is polar covalent, the way that I like to always use the analogy is if you've ever gone to out probably with a significant other or a friend and you ever decided to maybe split fries or dessert or something, probably a lot of the times, like maybe you might have had it even where you're each like cutting it down the middle, you're sharing it. And that's really great. However, some people might want a few more fries than the other one when they're not looking, and then all of a sudden it's uneven. So, and that's just how life can be sometimes. So, with that, we can draw that too. So, if I have carbon and oxygen, well, this means that the cloud is going to be more on oxygen because that has a higher electronegativity value. So when we show that, it's going to be more like little bit more teardrop shaped, and more of the electrons or the shading, which represents the electrons, shading electrons. So it's going to be a little more towards oxygen in this case. So it's going to be more heavily favored. Now, with fluorine, the last example, is just like if you're sharing with a little kid and they're taking the milkshake, they're obviously going to want all of it. So you're going to see a very uneven side of this. So fluorine has the highest value possible, which is a 4.0. Carbon has, once again, has that 2.5. So what we're going to do is we're going to subtract those two values. So 4.0 minus 2.5, and that's a 1.5 difference. So it's really, really polar and in favor of fluorine. So when we have that, how that's going to look, it's going to look very similar to the carbon-oxygen picture. But another way to illustrate that for everybody that might be struggling to understand this, it's very similar to a seesaw or a teeter-totter, where if I have carbon on one side and fluorine on the other, and this is my electron balance, well, we're going to have more of the electrons on the fluorine side in this case. So it's going to be very, very uneven. So, and what we can do with that is there's ways to label this and understand a little bit further. So this picture is very much like this one that I have here, where I have a chlorine who has a 3.0 value. You know it's more up and right to the periodic table as well, so it goes on the trend versus hydrogen. It's pulling or tugging all of those electrons towards it. So as a result, it's something where it's very, very uneven. Hydrogen just wants to share its electron, but it's like here you can have it, but it's pulling it away. So it's making it extremely polar as a result. So how do we illustrate this on bonds? So if I use, let's say, the picture above, the HCl, how can we show that for hydrochloric acid? So with this one, what we're going to be using is a couple different symbols. The first one is delta symbols, which look like almost like little music notes. So with this, so this is a delta, so Greek letter delta, and this shows partial charges. So keep in mind, this is not an ionic charge. So for this, it's very similar to like magnets, where there's a little bit of attraction between magnets, but you can still pull them apart. So with this one, the way that we would label it is we would look at the two values. So chlorine was a 3.0, hydrogen's a 2.1. So we can label chlorine as a delta negative and hydrogen as a delta plus, telling you that the charge is slightly more on chlorine. It's uneven. Okay. Another way for you to show this as well is using arrow notation. So let's say if I take HF, for example. So fluorine earlier had a value of 4.0. Hydrogen has a value of 2.1. So for this one, there's another notation which uses arrow notation. So what this arrow represents is something referred to as a dipole. So all these differences in charge. So the difference in partial charge is a dipole. Okay, so that's what that refers to, or a dipole moment. So whenever a molecule has a dipole moment, this creates polarity. Okay, so the way we can show this, we can use the deltas from before, or we can use a plus on the hydrogen, but remember this is a partial positive. So we then create an arrow pointing towards the fluorine. So this tells you that, okay, hydrogen has a little less electrons, but it's getting pulled towards the fluorine, and that's why the arrow is going towards that. Okay, so this allows us to be able to illustrate polar bonds by creating permanent dipoles, which is going to be a very important concept for the future when you start looking at intermolecular forces and trying to determine polar molecules. Okay, so now the biggest important thing to keep in mind is this is how you illustrate them, but you're going to be going off your periodic trend. So remember, the farther you go up and to the right of that periodic table, the more electronegative an atom is. So that's how you can kind of tell is something polar. So the closer is the fluorine, and the farther they are away from each other, the more polar they will be. This is Dr. Dan for this time. I hope this video helped, and please come in and tune in for my next video, which will be on part 2, which goes over the difference between a polar bond, which is what we talked about in this video, and polar molecules, which is putting it all together. All right. If you like this video, please consider liking and subscribing, and I hope to see you next time. Thank you so much. Bye. Have a wonderful day.